All right, welcome to Module 2. Picking up where we left off, we talked, we introduced biomechanics and we talked about how we're going to analyze human motion in order to optimize human motion so as to maximize performance and minimize the chance of injury. And we also said when we analyze and optimize, the first thing we do is we actually just look at motion in general. We don't look at the forces yet, even though obviously that's the key to biomechanics and the right adaptations, but we're just going to be able to, we need to be able to, I should say, to just describe motion. And that's what this module is all about. Module 2 is all about describing motion. And in physics, that's called kinematics. So in this first lecture, I'm just kind of introducing the concept of kinematics. We already mentioned it once before. We'll go a little bit greater detail right now and actually talk about not just kinematics, but also osteokinematics and arthrokinematics. We're going to have separate little lectures on each one of those. Because for us, for the human movement specialist, that's going to be really key because osteokinematics is really describing human movement and the direction of human movement. And arthrokinematics is describing joint movement. So start off right now. We're going to just talk about, once again, introducing kinematics. Then the next lecture, we're going to talk about osteokinematics. I actually will warn you, it's actually an adapted lecture of one I already did in the past. So it might be a little different, but you'll get the idea. So we're going to talk about osteokinematics, then we'll talk about the arthrokinematics, and then we're actually going to get into both linear and angular or rotary kinematics as well. So what do I mean by that? Well, let's look first of all. Types of motion, this is where that comes to, or it comes from, I should say. There are two general types of motion. There's what's called translational or linear motion. Well, think about that linear in a straight line, right? Well, there's actually a couple different ways of translational or linear motion. There is motion in an absolutely perfect straight line, and that's called a rectilinear motion. There's also motion along a curved line where all the points of an object move and follow each other along a curved path, and that's curvilinear motion. So there's rectilinear means a straight line, curvilinear means following a curved line. So there's translational, but then there's also rotary, or also known as angular motion. And what's that? Well, that is rotation about an axis, right? And that's, we're going to find out, it's usually measured in degrees or radians. And actually, when biomechanists usually look at it, when they're doing all the math, they usually do, it's actually radians that ends up working better. But from the day-to-day, when we look at things qualitatively, probably don't go radians. We'll talk more degrees, and yes, degrees are numbers. I just said qualitative. But when we talk just general joint motion, typically we tend to talk degrees. Trainers, coaches, physical therapists, and what have you. Biomechanists, when they're doing all their calculations, they use radians. Well, what happens if you put a rotary motion and a linear motion together? That's called general plane motion. And that's really how the human body works. If you think about it, I have a rotary motion here going about the axis of my elbow, and then I might have another rotary motion here from the shoulder, but then they kind of both move together and create this varied motion within a plane, and that's general plane motion. It's kind of two rotaries kind of creating a linear motion or a curvilinear path within there. So that's general plane motion. So those are the two types of motions. And going back to kinematics, we already defined kinematics as describing motion without regards to the forces that causes motion. So what does that really mean? Well, basically saying, okay, where is something? What's the position? All right? If it's moving, how far? Since we're talking about motion, how far is it going? So position, how far, how fast, how quickly, which is changing how fast it's moving, changing either the speed and or the velocity. All right, and that would be called acceleration, is what we're about to find out. So think of it this way. Kinematics is all about position. It's all about how, where it's at, how far it moves, how fast it moves, and how fast the speed or velocity changes. So going to the first one, position. We talk about position in biomechanics. Quite often, how do we describe it? Well, we'll often use Cartesian coordinates, the good old x, y axis, and you can see in the picture right here. And we'll, once again, use the coordinates of a Cartesian coordinate system to say this is where it is at this moment in time versus this other moment in time. Now we use X and Y axis. It might be position along the Y-axis versus maybe time. Position over as a function of time is actually very, very common, we're going to find out. So we're going to use these Cartesian coordinate systems. And for our usage, we're going to mostly stick with the 2D space. But once again, in the back of your mind, I want you to remember that we live in 3D space. So often we'll be looking at planar movement, but in reality, once again, we live in 3D space. We have to think three-dimensionally as well. We'll get to that. It'll all make sense as we move along here. So first of all, once again, there's position. We usually describe that in the XY axis. Then we have to say the change in position, all right? The change in position, once again, in relation to time. Where is it's at this time it's at point A, and at this time it's point B, all right? Well, when we describe the motion of an object, the change in position, there's two ways of doing it. There is displacement and versus distance. Now, displacement is a vector. Now, remember, vectors are straight lines, right? There's a straight arrow. And so think about it. If I have a start position and an end position, what we're measuring there is how far it went from point A to point B in a straight line. So if I have, say, I'm a triathlete, and I'm running the last leg, you know, I'm doing the Kona Ironman, and we see the start and the finish. Well, it's actually almost the same spot. It's actually not that far as displacement. But the actual distance I run, now here's the difference. Distance is a scalar, and it's the actual distance traveled following the path. Well, that's a full marathon, 26.6 miles. So distance is a scalar following the actual path taken. Displacement is a vector just from start to end position, all right? Well, certain times you're going to want to know the actual distance traveled. Other times it's going to be more important to understand the displacement, the actual vector, all right? So the big difference there between displacement and distance, displacement, once again, is a vector from the start position to the end position, straight line, while distance is the actual distance covered. If I jump in my car right now because I decide I want to go to Vegas, and I get in and I look at my little tripometer, it might say it's about 400 miles from my house, let's say. Well, if I actually get on a map and draw a straight line from my house to the Las Vegas Strip, it's going to be quite a bit shorter than that because it's not a straight path from my house to Vegas. So hopefully you kind of get that idea. Displacement, straight line, distance, the entire path. Now, let's talk about that as far as how fast you're moving. So think about it. If you have a 100-meter sprinter, the distance and the displacement would be the same because it's a straight line path, right? Well, let's talk about velocity now. Velocity would be how quickly, once again, it's a straight line path, from when the gun went off to they crossed the finish line. That's how fast they went, right? Well, how fast they went as far as speed would be the same at that point. Speed and velocity would be the same. Speed is distance over time. So once again, we see their speed, boom, same as velocity. Now let's say it's a 200-meter sprint. Well, now we're going to see actually 200 meters sprint, they're actually going around the bend of a track. Well, the actual distance travel is 200 meters, but if we actually do the math, we're going to find the displacement from beginning to end is quite a bit shorter. So their velocity would be different. Now, you might say, well, once again, velocity doesn't seem very handy. Well, it's going to come in very, very handy because we're going to find velocity really ties into motion as far as momentum and acceleration and forces. And velocity is very, very important. And where we're going to find it's really important is instantaneous velocity. So bear with me for a second, because if I know, if I get times for a sprinter, and I see, okay, it took them so long to run the race. Well, okay, that doesn't really tell me where do they need to improve. Do they need to improve in their starting speed right out of the blocks? Do they need to improve on their acceleration speed, how quickly they can get up to their max speed, or do we need to just improve on their max speed? There's different segments to a sprint. Once again, so where do I need to work? Do I need to work with them getting out of the blocks? Do I need to work on their acceleration, or do I need to actually just work on their top speed? Where are they weak? So let's take a second and think about a 100-meter sprinter, and let's say it takes them 10 seconds, exactly, 10 seconds flat to do 100 meters. Well, what does that tell you? Well, their average velocity would be what? 10 meters per second, right? 100 meters, right? They did it in 10 seconds, so their average velocity, 10 meters per second. Doesn't really tell you a whole lot. But let's say we could capture their position as a function of time using biomechanical tools like video analysis, as well as motion capture, that type of thing. And we could actually see, you know, every place, in milliseconds, well, maybe not milliseconds, an average camera usually will do anywhere from 23 to, say, 30 frames per second. So we could say 30 frames per second, we can get or even faster, they have high-speed cameras, and we could plot points exactly where they are several times a second throughout those 10 seconds. Well, then we get more of a curve that looks like this. And we can see their position in that little curve in relation to time. Well, what does that tell you? Well, now we're getting a little bit more information now as far as how fast they're going at any moment in time. Now remember, average velocity is what? I just said it. It's the distance traveled over that particular amount of time, the average distance traveled over that amount of time. But let's say I took a smaller window, okay, and now I'm looking at that curve, and instead of looking at from beginning to end, I look at just from, say, the 2-second mark to the 3-second mark. Well, now I can actually, once again, take the average velocity just from 2 seconds to 3 seconds. Well, that's good, and if we look at that now, that line now follows the curve a little bit closer. Now let's say if I go from 2 seconds to 2.5 seconds. Well, once again, now I have that straight line velocity, and it's getting closer and closer. That line is getting closer and closer to that curve. And really what we're doing is we can go closer and closer and closer until it's near instantaneous. So basically what we're doing, they call it taking the limit as it goes towards 0. It's getting very, very close to instantaneous. What is this? This is calculus. Don't freak out that I said the word, but we're basically taking the derivative here in order to obtain instantaneous velocity. And this is so key. The instantaneous velocity at any point in that curve is basically the slope of the tangent line at the curve. You might be freaking out on the math. Don't worry about it right now. Just think if I could just take a point on that curve and I could just draw a little line, that slope right there tells me exactly how fast they're going at that instant in time. And wouldn't that be really important to know? How fast are they at 0.5 seconds, how fast they're moving, versus 1.5 seconds? So we can see then, once again, how much they're increasing their velocity. All right? So this is a big deal here, is that basically instantaneous velocity is the derivative of the position over time as a function of time. So instantaneous velocity is really, really important when we get to quantitative biomechanics. Right now, once again, I'm not going to test you on any calculus or anything like that, but just kind of get the idea of it'd be really nice to know, don't you think, at that moment in time, that instant, how fast they're moving. Well, that goes to calculus a little bit, and that's that instantaneous velocity. Well, that's important, but maybe I don't care just about the instantaneous velocity. What about how much they're accelerating? What is acceleration? Acceleration is change in velocity over time, right? It's change in velocity, how quickly they're changing speed, and how quickly they're changing velocity, I should say. So that's what acceleration means. Now, I'm going to put a little star here, a little asterisk in your mind, okay? Because whenever we say acceleration, remember we're talking kinematics at this time, which means we aren't thinking about forces. Well, we are going to think about forces a little bit, because what we're going to find out is that what causes acceleration of an object are forces. That's what causes acceleration. This is what causes objects to change their momentum, objects to change their velocity is is a force on the object, all right? So even though we aren't talking about forces yet, in a way we are, because as soon as we say something's accelerating, we can say in our minds, boom, right there, something's accelerating, that means there's a force on it. And remember, forces are what cause all the cool adaptations and possibly negative adaptations to the body, right? So acceleration is how quickly we change velocity. And once again, we can look at average acceleration over time. So we could look at, in the case of the sprinter, we can say, okay, at 5 seconds they were moving at this velocity, and at 10 seconds they were moving at this velocity. Well, were they going faster or slower? Maybe did they peak out at 5 seconds and they were actually slowing down by the time they hit the finish line, or maybe they were still accelerating. Or if they were going at the exact same velocity, that means that's zero acceleration. Let me say that again. If they're going at the exact same velocity, well, that means there's no acceleration there between those 2 points in time, no average acceleration. But guess what? We can graph out velocity just like we did position. We can graph out the velocity in relation to time, because we can get those answers from position. So if we know where they are at as a position, as a part of time, as a unit of time, guess what? We can then determine their velocity. And if we know their velocity as a point of time, we can then see their acceleration. So all we need to do as far as data, okay, if we're once again looking at a sprinter, all we need to know is their position in relation to time, and then we'll also know their velocity at any moment in time, and then we'll also know their acceleration at any point in time. Whew. All right, I know there's a kind of mathematical concepts there. Please go over your manual and look at the connection between, and these kinematic connections between position related to time, velocity, and acceleration, right? Now, units of measurements in this course, I'm going to probably mostly, once again, stick with the metric system. I already mentioned that. So when we're talking position changes, displacement, we're talking changes in position as relation to time, which is velocity and speed. We're going to be using meters and seconds mostly, all right, just because the math really is easier. A couple other things, going back to velocity and acceleration. Now, bear with me for a second. Can I have a positive velocity and a negative acceleration? Absolutely. Think of it this way. You actually determine which direction is the positive direction when we're doing the math here. So let's say we're talking about a football player. And what position is going to be positive? Well, it's going to be going upfield, right? Going for the end zone. That's positive. That's the positive direction. Well, negative direction, obviously, would be going the wrong direction, going backwards. So I could be running upfield and going positive velocity, but all of a sudden, I get hit by a force coming at me, someone trying to tackle me. And let's say he hits me hard, but I'm still moving forward. Well, I'm still moving forward, so I have positive velocity, but I have negative acceleration, so negative acceleration is slowing me down. Now, can I have a negative velocity and a positive acceleration? Yeah, I can. Let's still go on the football field here. Let's say I'm a running back, and I get the ball, but my lineman didn't do the job. And as soon as I get the ball, someone's here tackling me, and he's moving me backwards. And so I have a negative velocity, all right? And probably initially a negative acceleration going this way. But then my force, I'm slowing him down. In other words, if I just let him go and carry me back that way, we keep going, but I slow him down. So it's a positive acceleration in the negative velocity direction. Hopefully that makes sense. Let's think of it this way. If I go to a side movement this way, and we're going to call this the positive direction, and what happens is I accelerate, pushing off right now my left leg. I'm accelerating this way, and so I have increasing velocity, increasing acceleration. But then I land over here on my right leg. I'm still moving this way initially, and I'm negative acceleration. By the way, in general layman's terms, we would call that what? Deceleration, right? Negative acceleration. Technically, in physics, there's no such thing as deceleration. It's a negative acceleration, but we'll use the terms interchangeably here. So here this is the positive direction. I accelerate pushing off. Okay, I accelerate pushing off with my left leg. I go through the air, and then I land with my right leg. I negatively accelerate. I'm still traveling this way a little bit. And then still negative acceleration. And then eventually I change directions, and now still negative acceleration, negative velocity, because I said this is the negative direction. Then I land on my left foot over here. I have positive acceleration. I'm still initially moving this way, and then I change directions this way again, and now I initially have negative velocity, but a positive acceleration due to this leg, until that acceleration, that force is enough to change my directions again. So I'm now back to positive acceleration, positive velocity. I know that's a little tricky. That's a bit much. Read the book. It does go over that a little bit, quite a bit. That's a big deal, actually, when we get to forces and that landing movement, foot strike and running and so forth. You're going to talk about being able to negatively accelerate or decelerate and then turn around to positive acceleration. That's a big part of actually developing power, actually, is being able to turn that around from a negative acceleration and then to a positive acceleration. All right, we're actually going to get more into linear, and that was all linear kinematics. And we're going to actually get more into linear kinematics later. But I kind of wanted to introduce it to you a little bit. Once again, I'm going to kind of review all the same stuff again. But the next video is going to be talking about describing human movement, osteokinematics. And once again, it's a video that I'm borrowing from another lecture I've done in the past. So you'll see a different shirt, I guess. Hopefully you don't mind, but it's all the same stuff. And after that, we'll talk about arthrokinematics.